Welcome to the analytical corner of in-depth mechanical engineering and manufacturing. The bike owner is struggling with the traditional chain and freewheel drivetrain, which causes kinetic energy loss. A breakthrough improvement idea was sparked. Let's see how the expert modifies this structure. Back in the workshop, the first material is a large, rusty three-spoke cast iron flywheel. An angle grinder is fired up to remove the outer rim, keeping only the hub and the three load-bearing spokes. The friction cuts create intense sparks. The cut surfaces are ground smooth to ensure balance. An impact wrench is used to completely remove the original crankset. The square taper bottom bracket spindle is exposed. He is looking for a compatible mechanical adapter. A hex nut is used as a spacer, tightened directly onto the bottom bracket spindle's threads. The three-spoke flywheel is installed. Manual threading temporarily secures the pulley assembly. A steel hammer is used to firmly tap and center the spindle, followed by an impact wrench to lock the retaining bolt. Checking the concentricity of the rotating system. Next is high-intensity arc welding, permanently welding the crank arm to the flywheel to create a seamless primary drive unit. A steel pipe is used for alignment to balance the axis, completely eliminating any wobble in the system. Flipping the bike over, the next step is a deep intervention into the rear wheel axle, where the torque is received. Dismantling the drum brake mechanism. The axle anchor bolts are loosened with a wrench to release the rear wheel. The metal chain is cut apart with bolt cutters, marking the end of the old drivetrain. The rear wheel is removed from the dropouts. A chisel and hammer are used to tap and loosen the threads. The multi-speed freewheel and cogs are completely removed from the aluminum hub, preparing to install the new system. Starting the fabrication of the power receiving assembly. A thick cylindrical steel pipe is clamped tightly in a machinist's vise. An angle grinder cuts a short section from the steel pipe to create the outer sleeve for the bearing housing. The steel pipe component is deburred. The inner surface must be smooth to fit the load-bearing bearing. A large industrial bearing is test-fitted into the steel sleeve. The machining tolerance is extremely tight. Clamping it back into the vise, the angle grinder is used again to chamfer and flatten the surfaces of the cylindrical pipes. Taking a threaded ring from the core of the old freewheel, he continues grinding to reduce its outer diameter. Grinding the threaded edge aims to make it fit perfectly inside the inner race of the industrial bearing. The small threaded bushing is pressed into the steel blank. The continuous grinding process requires high precision, checking the connection of the bearing and steel sleeve components. The secondary drive assembly is gradually taking shape. Tack welding the threaded piece to the bearing's inner race. The high heat melts the metal to bind them together. Using a wooden block and a hammer to slowly press it in, the steel sleeve fits tightly onto the bearing's outer race. The old freewheel core is reused and hammered tightly into a multi-layered V-groove pulley assembly. Welding the freewheel assembly in place, then integrating the newly fabricated bearing unit into the center position. Fully assembling the secondary drive unit. Manually threading it onto the hub axle. The freewheel pulley assembly is tightened concentrically on the rear wheel spokes, replacing the old chain freewheel. Test fitting the wheel onto the frame. The expert uses a marker to mark a spot on the chainstay. The powerful angle grinder completely cuts through a section of the lower frame, creating a gap to thread the drive belt. The rear wheel is put back in position. An arc welding machine sturdily reconnects and reinforces the frame. The mechanical drum brake system is reassembled, attaching the brake arm, hooking the spring, and threading the brake cable. A wrench tightly secures the rear axle nuts, ensuring the wheel spins smoothly and engages perfectly. Spin testing the wheel to check the rotation momentum and noise. The hub works perfectly without any excess friction. The most important step: threading the ultra-durable Coro V belt through the newly created gap in the frame. The belt is tensioned, fully wrapping around the crank pulley and the rear hub pulley, forming the new drivetrain. Hand testing the momentum, the crankset rotates smoothly. The belt grips the grooves exceptionally well, transmitting torque instantly. Flipping the bike upright completes the assembly phase. The chainless bicycle is ready to roll. The mechanical parts are electrostatically painted silver, enhancing aesthetics and providing perfect rust prevention. Test driving it in the yard, there are no more rattling noises. The bike glides along smoothly thanks to the smooth belt drive. Heading out to the main road to check the actual speed. Light pedaling, yet the bike achieves impressive acceleration. Close-up shots show the belt and pulley system operating smoothly. The new transmission ratio helps optimize the pedaling force. Viewed from a motorcycle riding alongside, the speedometer records an incredible number, 33 kilometers per hour. An incredibly creative mechanical modification, turning a rundown bike into a smooth speed machine.